Hey everybody, Scott Henson here. I'm going to do a quick demo and tutorial on calibrating a EasyZ CV100. The process is the exact same for the CV1K, but you'll probably have to do it at slightly higher voltage, maybe 10 or 15 volts, because the voltage attenuators are so strong in the CV1K versus the CV100. I'm using a 10 ohm resistor. We'll get into that in a second. You do need a power resistor, a non-inductive power resistor, to serve as the load for calibration. You can't calibrate with a speaker. And the reason calibration is important is because we have to do some post-processing. You're dividing one channel versus the other to measure impedance. And since there's a division, if there's a channel imbalance, that will be added to or included in that division and mean that your measurement will be incorrect. So I typically try and get within 0.01 dB. That's how I calibrate them here after I make them before I send them out. But the closer you can get them, the better. 0.5 dB is definitely not good enough. 0.05 dB you might be willing to live with. That's like 0.1 ohms for a 10 ohm resistor and things like that. I try, as I said, try and get them to within about 0.01 dB. It's actually not that hard. It takes only about 30-45 seconds. So let's do that calibration now. First thing to note is that when you do these impedances measurements, you want to keep the full IR. I believe REW comes default with this at 1.7 seconds. We want to keep the full IR. That gives us a longer available impulse response to do that FFT on. Gives us good low frequency resolution. If you didn't have this, you would have the impedance at low frequencies would sort of bounce around, and that's an artifact of the measurement, and it's not really what it's doing. 2 seconds 2 second FFTs gives you enough resolution, enough ability, and down at low frequencies to get below 10 hertz, which for most uses would be fine. So again, keep full IR. The window shape doesn't matter all that much when doing these. It's not like you're canceling out reflect or you're not windowing in the middle of a reflection. It's a very clean signal. I'm using the Focusrite 2i2. All right, so let's do this. Oops. First thing, I'm clicking on all the wrong things today. Generator. So I've got it set up and I've already done this calibration. It's going to put 5 volts out at 1 kilohertz. And let's check to see if these are exactly 20 dB apart. Again, I'm using a 10 ohm resistor that I measured on a very high precision 4-wire DMM. They are not 20 dB apart. It should be minus 46.24, bouncing around, to minus 26.24, bouncing around. And right now, it's not. And I need to change that. So there is a small calibration potentiometer right next to the 1/4 inch TRS outputs on the unit. And I'm going to, since I need more signal, we're going to go to the right. And this is a 20-turn potentiometer. So you have very good resolution here to get that. All right, it's about as good as we're going to get that. So now that was it. That's our channel calibration. If you change sound cards, do it again. There's enough differences. If you have a sound card with a digital attenuator like a Roland Octacapture, over its range, gain range, you probably, every time you change that gain digitally, you'll probably want to check this calibration. All right, so we can stop hitting that resistor with 5 volts. So the first thing we're going to do is measure voltage. That's the left channel on this. It'll be silent because it's into a resistor. All right, so there's the frequency response of my Mackie FR1400 driven, or the sound card goes through a DBX PA2, then into the 1400. So this low frequency roll off I'm not really surprised at. as long as it matches channel to channel, it'll cancel out. So let's go measure current. And that is definitely current. You can tell by the lower signal level. All right. So I'm going to, for the sake of my forgetfulness, voltage, current. All right. I'm going to export these as CSVs, units, SPL, comma separated. Don't include any comments or headers in the export. Example B, I've already done this once or twice, so this is going to have to overwrite. File. Export. Example I.csv again exists. Now I'm going to switch over to my okay, interesting error. Just going to save it again. All right. All right. This is the problem with doing real-time demos. Okay, we're not recording this thing again. I've already tried too many times. This mistake is the least of my worries. Here we go. So I am going to run this example 1.cv.csv, example 1i.csv. This Python program will then take the two files, calculate the impedance. All right, this is about what we're going to get. Now, I use the plot library here. I may have it do this plot so that I can double check to make sure that everything is all right. And this worked this time. So that's good. And what you see here is that this plot starts at 1 hertz. So this is 10 hertz. And you've got a 10 ohm resistance down below 10 hertz. So it is working. And remember when I said down at low frequencies, it can go a little wild. And that's what I was talking about, right? So longer FFTs and getting more things out of this signal path would allow me to get even lower. But in this case, for most purposes, getting down to 10 hertz would be great for loudspeaker development. This noise, this is part of the input noise, and when you plot this at 1/48th octave smoothing, you're going to see that this all goes away, and that has very little impact on even high Q speakers. So let's go import this in REW and take a look at it. All right. So, and now I'm going to go 48th octave smoothing, and lo and behold, now we've got an excellent measurement. You can see that the phase rotation due to the channel frequency response canceled out nicely. Nice and flat phase response, nice and flat impedance here for this 10 ohm resistor. So that is how you make an impedance measurement. So let's go. I'm going to put you on mute for a second. This is going to be great YouTube video. And I'm going to put you on mute for a second, and I am going to go change and hook up to an actual loudspeaker so that we can measure a loudspeaker at a couple of different drive levels. Okay, I'm back. Did you miss me? Probably not. Okay, so we are going to do the exact same thing we did. Got to measure it once for voltage. I'm not worried about heating. If I'm getting really worried about heating, I'll measure current first because that's what changes as the voice coil heats up. But at 2.83 volts, this 8-inch woofer is just not going to heat up that much. It's got a 2.5-inch coil on it, so I'm not too worried about that. So we're going to do voltage first, and this might be a little loud, so I'm going to mute while it does this sweep. All right, I'm back. Now I'm going to do the right channel, which is the current. Okay, now you can see where the SPL response of that current channel is really interesting, right? So this is making a measurement of that current. This is the free air resonance of this 8-inch PA woofer. And you can see that the current draw is lower. Let us export these. 8283V SV. Hopefully I'll remember these file names. Eight 283i.csv. Go back to here. Run this 8_283v.csv. 8_283i.csv. And yes, I talk to myself all the time. All right. Interesting little phase thing happening there. Investigate that. Again, the fun of doing this live. But that may just be because we don't have enough resolution. All right. Okay. So, oh, yeah, it's just a pie plot problem, not a real problem. All right. So now I'm going to go to all SPL impedance, clear selections. We'll get the most recent one, limits, fit to data, and look at that. That is a smoothing. That is a very good measurement of that 8-inch driver at 2.83 volts. And you can see how well the system does. Now, you can do that kind of thing with even the USB style measurement devices. The real advantage of the CV100 is when you want to test at higher voltages. So you can start looking at driver impedance shifts with drive level, things like that. So let's do that real fast. Again, I'm going to mute you because now it's going to get really loud. And yeah, we don't want to blow anybody's ears out. So measure. This is going to be exciting. It'll be loud for me too. I have in-ear monitors in, but I'm still not looking forward to it. Go voltage first. I'm back. All right. Let's put this on. Text 8.6 volt .csv. Text 8.6 volt I.csv. My naming conventions are not good, but that's all right. As long as I remember what I called them. 8.6, is it underscore? long as I have no memory whatsoever these days. 8, 6. Hey, I did. I remembered correctly. Still got the little pi plot phase issue, but that's all right. I'll dig into that later. Let's import that. Smoothing. All right. And this is the sort of thing that makes this so valuable. Now, this particular woofer is a very expensive, very high-end 8-inch Pro Sound driver, and the difference between 2.83 volts and 6 volts is pretty minimal. These woofers spend very little time at these drive levels. A couple hundred watts, not 4 watts, right? But you can already start to see the shift in resonant frequency down with drive level, and that is exactly what you tend to see. And on a low-cost driver, a small driver that is, you know, a small full-range driver that's not meant to handle these kind of powers, this shift will be large, and it is a way to evaluate whether or not you'll be able to keep that frequency response that you want, that bass alignment in that enclosure that you want, by looking at this shift over drive level. The other thing you can use this for, the CV100 for, I'm going to go back to this distortion, or this measurement, and look at the distortion curve. Now you can see where you are measuring the harmonic distortion of the current through the motor. This is, the first time I ever saw this was the Purify folks. They do this. This is a pretty low distortion motor. What this tells you, in my experience when I first saw it, I was like, okay, well, getting motor current distortion is kind of helpful, but what does it tell me? And what it tells me is that the distortion floor is not going to be any better for the full speaker. The suspension can only add to this distortion. It's really not going to be taking away from it. So if I measured the distortion of the speaker at acoustically, it would be a little bit worse than this, right? You can also use it to check distortion shifts over drive level. It's to the drive unit manufacturers, this second, third harmonic, you know, which one's dominating and stuff like that. That actually tells them things about their motor structure. I'm not going to get into that. It's way too much for this video, and this video is already way too long. Some quick tutorial I made. But this is another thing you can do with the CV100 that is incredibly useful, is you can start comparing motor linearity between different manufacturers that you might be considering for a project at different drive levels. This one does a very good job. This is actually a pretty good measurement for an 8-inch woofer in free air, right? So at 6 volts, you're still seeing a bit of excursion down at these levels, but this is pretty good. All right, have a good day, everybody. Thank you. Bye.